Okay, problem number 15. In this problem, we are given a table of daily death rates from the SARS virus in Singapore at 2-week intervals in the period from March 1st, 2003 to May 24th, 2003. And we are asked to estimate the total number of deaths from this virus in Singapore in this time interval using left endpoints of the 2-week intervals. So first of all, let's recall how we could calculate the total number of death rates in any time interval, also, and in particular in this time interval, given the death rate. The general principle which we use for this is the fundamental theorem of calculus, which says that the total change in some quantity over time can be found by integrating the rate of change of that quantity with respect to time over that time interval. So if the daily death rate is given by some function capital R of t, I have it here, this function right here, then we could find the total number of death during this time interval by integrating this function R of t, which is a daily death rate, over the time interval from 0 to 84. This time interval from 0 to 84 is the time interval that we are looking at in this problem, because we have 6 2-week intervals, so 12 weeks total, considering that each week is 7 days. 12 weeks equals 84 days. And so we are integrating the death rate from 0 to 84 to find the total number of deaths. Now, note that we're not given the daily death rate at every moment of time during this time interval. We're only given 7 readings at the time intervals, at the moments of time specified in the table: March 1st, March 15th, March 29th, April 12th, etc., to May 24th. And so we can't really calculate the exact number of total death from SARS in Singapore over this time interval. We can only approximate, and our approximation is going to be obtained by looking at the Riemann sum for this definite integral. Now, there are different kinds of Riemann sums. We could use left endpoint Riemann sums, right endpoint Riemann sums, midpoint Riemann sums. There are also other kinds of Riemann sums, but in this problem we're told to use left endpoint Riemann sums. And so how do we construct this Riemann sum? So in general, if we have, I drew here schematically a graph of this function R of t, the daily death rate. Just a schematic graph, it's probably not going to match the numbers in the table, but it's not that important for our problem. I just wanted to indicate the principle that we use. So we have a function R of t, which represents the daily death rate, which varies with time, and the total number of deaths would correspond to the area under this death rate curve, which is also the integral from 0 to 84 R of t dt. And so essentially what we're trying to do is we're trying to approximate this area under this curve. Now, we don't have an equation for the curve, and we only have essentially points, right? We have this point here, this point here. We're given some points. We're not really given the curve. So based on these points, what we can construct are the rectangles. And these rectangles will be approximating the region below the curve, the death rate curve, and above the t-axis. The base of each of these rectangle is the same. It's an interval of length 14 days, a 2-week time interval. So all of our rectangles will be having the same width of 14. Now the height of each rectangle is going to be determined by the value of the death rate function in the left endpoint of the interval. So for example, if we look at the first segment right here from 0 to 14, t equals to 0 corresponds to March 1st, t equals to 14 corresponds to March 15th. We have a reading for March 1st for t equals to 0. The death rate at that point is 0.0079. And so since we're asked to use left endpoints, we will make our first rectangle to be of height 0.0079. In other words, what we're doing here is we'll be assuming that for the first 2-week interval, the daily death rate stays constant and equal to the death rate on March 1st. In other words, it stays equal to 0.0079. And the area of the first rectangle will be approximating the number of deaths during that first 2-week period. So, calculating the area of the first rectangle, we will be multiplying height and width. The width is 14. That will be the same for all our rectangles. And the height of our first rectangle is 0.0079. Multiplying 14 by 0.0079 will give us approximately the number of deaths from the virus during the first 2-week interval. Now, of course, it's only approximation because in reality, probably the daily death rate did not stay the same during this time interval. Maybe it's gone up, maybe it's gone down, probably it's gone up. Actually from the table we see that it goes up consistently from March 1st to March 15th to March 29th to April 12th, April 26th. And on April 26th we have the highest daily death rate, so the graph goes up all the way to April 26th. And then it starts coming down. Now, we do exact same thing for our second, third, fourth, and fifth and sixth rectangles. All of them have width of 14, and the height is determined by the value of the death rate at the left end point of that interval. Here's the calculation for A1. Here's the calculation for A2, the area of the second rectangle. Repeat these calculations for all 6 of our rectangles. The last one has a height of 0.4630. This is the death rate on May 10th. And the total number of deaths during this 6 2-week intervals will be equal to the sum of these approximations, A1 plus A2 plus etc. plus A6. Now, all of these areas are equal to 14 times height. We can factor out 14, and so our approximation will be 14 times, in parentheses, the death rate on March 1st, 0.0079, plus the death rate on March 15th, 0.0638, etc. We will be adding here all the numbers from our table except the last one. We stop at May 10th. May 24th reading is not included because that's the right endpoint of the last interval and we are using left endpoints. Plug this in a calculator, get the result and round to the nearest integer, and you should get 24. and that is the approximate number of people who died from SARS in Singapore during this 6 2-week intervals. That, of course, is not the exact number. It's only approximation, and probably not a very particularly good approximation, because the 2-week intervals that we use are fairly long. There was probably quite a bit of variability in the death rate, daily death rate, during each of these intervals. So when we make an assumption that the death rate stays constant, which is the assumption we use to build our rectangles, probably we're making a significant error there. But anyway, this is how you would approach this problem.